So last time we talked about thermal equilibrium, and before I get into that, let me just remind you of our heat equation model. So here we have this equation, which describes the heat equation model. So let's think about what the variables mean. So U here on both sides, left and right-hand side, is the temperature. The solution we're looking for is U of xt. And from a Calc 3 point of view, keep in mind that U is a multivariate function. U is a function of x and t, and we can interpret it as a surface over the space-time manifold. So on the left side here, we have the derivative of this is the rate of change of the temperature with respect to time. And on the right-hand side here, I have the rate, the second derivative of U with respect to x, which is the spatial variable. I think of it as kind of if you think of the temperature on the temperature gauge, its movement would be velocity. And so I kind of think of it as an acceleration, but you have to be careful and keep in mind that U is temperature, not position. And K is just, it's a parameter. It's called the diffusivity constant. So yeah, this is the heat equation. We're trying to solve for U. It's a PDE. There's more than one variable involved. And now there's this physical reality of temperature that many systems involving temperature, over a long period of time will find some type of steady state or thermal equilibrium, resting position. Not necessarily true. That's not true for all systems. We can think of examples where there is no steady state temperature, such as the case with blinking lights. And we'll come back to this. We'll analyze the blinking lights case mathematically in a couple of slides here. So we started by just solving a baby problem. We said, okay, so what would the thermal equilibrium or steady state solution look like? So we assume that, I should say, one thing I should mention with the thermal equilibrium solution, what's very important is the idea that over time, our temperature, U of xt, our solution to the PDE, will over time, in a limit as t goes to infinity, evolve into the steady state temperature function. So eventually, as time goes to infinity, the pizza gets cold, the temperature gets stabilized, time is no longer a factor in the temperature situation. Okay, so in our model, so this part is very subtle, and of course we'll come back to this many times. In our model, we will assume the temperature U that is in our PDE has this type of structure where it's got this U bar of x, which is the steady state solution, which is the long-term temperature behavior, plus what we call a transient solution. So V of xt here, we'll call this the transient solution. And it accounts for this kind of the short time behavior of the temperature. And what we expect, so that everything fits with reality, is that as t goes to infinity, the transient temperature will decay to zero and no longer be a physical factor in the dynamical behavior of the temperature in its steady state, in its resting state, in its equilibrium state. So yeah, so we tried a baby problem. Let's just try and find what the equilibrium solution might look like. So we assume, suppose we have a solution U that's not dependent on time. So here, if I assume U is not a function of time, then in my heat equation, on the left-hand side, the partial U partial T will be 0. And then our PDE becomes a DE, a differential equation. And integrating twice, I can find the answer. And then if we assume some boundary conditions, we can solve for the constants, and we can come up with a solution for the steady state or equilibrium solution of the system. So this is what we expect when t goes to infinity. We expect this to be the limiting function of U of xt, the solution to the heat equation. And once we found, just as a random side comment that might be relevant for the homework, once we've found the steady state solution, we can use the steady state version of Fourier's law of heat conduction to find the steady state heat flux. So what do I mean, the steady state version of Fourier's law of heat conduction? Fourier's law of heat conduction in its original form depends on two variables, on x and t. So here we should have u of xt. So this is the one variable version where we're assuming t is not a factor. And remember what Fourier's law states is that the heat flux is proportional to the temperature difference. So the greater the temperature difference, the greater the heat flux, the magnitude of the heat flux. And the minus sign is because the heat flux goes from hot to cold, and the derivative typically, the rate of change, that's describing the rate of change when you go from cold to hot, so it's kind of a reversal of directions. But so yeah, we can use the steady state solution to find what we call the steady state heat flux. How is the heat flux behaving, as t goes to infinity? Evan.
Yeah, I had a question. So the heat flux is the change in temperature with respect to position, right?
Yeah, per unit surface area, yeah.
Okay, so it's possible for there to be differences in temperature in different positions, but no heat is flowing time-wise from one position to another, right?
Something like that, yeah.
Okay.
Yeah. Yeah, the physical part of it is sticky, and that's the part we always have to kind of try and train our brain to understand the physical part. Thank you for that question, Evan. So let's do another steady state calculation. Let's assume in this case we have an internal source of energy, and let's see what conditions need to be true of the internal source of energy so that there actually will be a steady state solution. Okay, so think about the blinking holiday lights, which has no steady state solution, because when the light is on, the temperature is being heated up of the bulb. And then when the light is off, the temperature is cooling down. And then, so it's always going up and down, up and down, up and down. Okay, so here we assume we have some heat source, internal heat source Q. And then as before, assume U is just, that should be an X. That's a typo. So hold on. Assume U is not dependent on time, that it's a function of X only. So I'll have to fix that, folks. And then, so in our heat equation, the partial U partial T part becomes zero. The derivative on one side of the equation becomes zero. So that's where this zero right here is coming from. And so before on the previous slide, we'd assumed Q was zero. Now we're not doing that. And so now I'm going to move the Q over, and of course the PDE will become a DE. I'm going to move the Q over and divide by K. And then, so now what we see, we can integrate twice, but even before integrating, you can see on the left-hand side, I have U, which is supposed to be a function of X only. But on the right-hand side, we see the appearance of the variable T. So as it stands right now, without any further restrictions on the internal heat source, there's no guarantee of a steady state solution. The only way we can get a steady state solution is if this T variable is not here. That's the only way we can get a steady state solution. So another way to say that is if partial Q partial T is not zero, then there will be no steady state solution, as with the blinking light scenario. If we want to have a steady state solution, then our internal source of energy will have to be, time independent. Partial Q partial T will have to equal zero. It'll have to be constant in time for a steady state solution. That's just what the analysis is telling us here. And that's fine. That's just part of how our model works. So let's go ahead and assume now for the next example that we have an internal source of energy. And it's just, let's say here it's not even dependent on X, just that it's a fixed constant, not even dependent on X.
Dr. Bott?
Is that a general property? What's it, Jeffrey, in your question? On T, oh, on T, yes, yes. So here, this analysis is basically implying that if our system is to have a steady state solution, and if we have an internal source of energy, then that internal source of energy has to be time independent. That's what this math is telling us with respect to our model. Now, was there a question?
Yes, Dr. Bott.
Yeah.
What do we call it if there's a periodic, not steady state, but in your blinking Christmas light example,
What do we call
that
equilibrium state? Yeah. I mean, it would just be, I mean, I'm sure there's a term for it. I don't know. It would be some type of periodic equilibrium state or something like that. But that's a great question. I should probably look that up at some point.
Thank you.
But yeah, you know, that would be now kind of a different avenue of analysis. And certainly, you know, a problem we should tackle after we've tackled the easier problem in terms of, you know, intellectually approaching it and breaking the complicated problem down into baby steps. Yeah, so the asymptotic behavior of these systems is, you know, a huge area of research. But yeah, yeah. So here, let's assume the internal source of energy is a fixed constant. And so now we have this equation as before. I'm going to move the M over, and of course the PDE becomes a DE, right? Since we have you know, no dependence on T. So that's what I did here. I just changed the notation. And then now we're doing our usual, you know, integration, our usual calculus, integrate twice, you know, keeping track of our constants of integration. As I said, this is second order in the spatial variable. So we have two free variables, free constants. And so then we assume some boundary conditions as we did before. You have T1 on the left and T2 on the right. And so then if you solve for the constants, you get this solution here. It's a quadratic. So here are the boundary conditions I'm using. And so then, you know, we use that information to solve for C1 and C2. And you can see if X is 0, C2 is going to equal T1. So that's where this is coming from. And if X is L, there's a little bit of algebra to do, and I'll let you work that out. And so here we get this solution here. You know, keep in mind T1, T2, M, and L are all known. So here we know this steady state solution, and it's a downward facing parabola. And just for kicks here, I graphed, you know, an example of it for some choice of those parameters. So you'll see this kind of stuff on the homework that's due on Friday. This, you know, so this would be part of a two-part process for solving a PDE. So so let me just remind you, you know, what do I mean by two-part process? So essentially, our belief is that U, the temperature that we're looking for, the solution we're looking for, is made up of this equilibrium solution and transient solution. So we've done examples here on these slides of how to find the equilibrium solution. What I'll show you on Wednesday is how to find the transient solution using separation of variables. And then when we put these two solutions together, then we'll have cobbled together, we believe, a solution of the heat equation. Why do I say we believe? Because the second part of differential equations, or PDEs, definitely PDEs, is we have to verify our solution. We have to, in fact, make sure that when you know, that it satisfies the heat equation, that it satisfies the boundary conditions, that it satisfies any initial conditions. Okay, so you kind of should keep the big picture in mind as to how the equilibrium solution is coming into play here. We'll find, so typically with a standard PDE, like a standard heat equation, we'll find the equilibrium solution, we'll find the transient solution, we'll put them together, we'll verify that it's a solution, and then we'll do our dance of happiness and rejoice, right? So, so let me talk about, the insulated boundary condition situation. Okay, so in terms of big picture, we're still talking about equilibrium solutions, but I want to do the case where we have insulated boundaries. What's called a Neumann boundary conditions, where we're giving boundary conditions for the partial derivative. Okay, not u. So here, how this is different from what we did before is we have this type of boundary condition where information about partial u, not information about u. So here, by the way, here's a full-fledged PDE. This is what if someone gives you a PDE, you'd expect to see certain things. So I'm expecting to see the actual model. Pay attention to the domain. X is strictly in between 0 and L. T is strictly greater than 0. And then we have here, so pay attention here, the initial condition. So initial condition, this is specifically referring to, the time variable. So this is information at t equal to 0. That part's important. That's why we call it an initial condition. It's information where the time variable has been replaced with a constant. And we've got the information, the initial information. So look here, look at this. Here, t is greater than 0. And here, when t is equal to 0, we know all the information, we know all the information across the entire rod. I'm asking you to compare the domains. Like here, in the PDE, x is strictly between 0 and L, and t is strictly greater than 0. When t is equal to 0, the initial condition gives us information about what's happening when t is equal to 0 across the entire rod. F of x is known as the initial temperature distribution. And then the other thing we're expecting to see in a well-defined PDE is the boundary condition here. Of course, we've talked about many different types of boundary conditions. So here we have this boundary condition where they're giving us information about partial u. There's many forms here. There's Neumann boundary conditions, there's Dirichlet boundary conditions, there's Robin boundary conditions. There's many different types of boundary conditions. Okay, so we're just kind of learning and again, look at the domain. Look at the domain here. This is for t greater than 0. And look at the spatial variables. So in the original PDE, it didn't say what's happening when x equals 0 and x equals L, right? This is a strict inequality here. Look, the boundary condition is telling us what's happening at x equal to 0 and x equal to L. And then look, this is for t greater than 0, because t equal to 0 is already being covered. What's happening at t equal to 0 is already being covered by the initial condition. So PDEs is complicated. There's many moving parts. Just to be able to understand the problem's formulation took us 3 weeks of work, 4 weeks of work. Just to understand, the question. Yeah, go ahead.
Do we need an IC and 2 boundary conditions or an IC and 1 boundary condition for this to be fully specified?
We need, so since there's two spatial derivatives, from how I understand it, is we would need 2 boundary conditions, because there's 2 spatial derivatives. That's how I understand it.
Okay.
Evan?
So you need 3 pieces of information total if you're using Neumann.
Yeah, right. Well, I think you need 3 pieces of information in general. You'd need an initial condition and at least 2 boundary conditions always.
Okay.
Either information about u at the boundaries or partial u at the boundaries.
Gotcha. Thank you.
Evan? Did you have one?
Yeah, I had a question. So boundary conditions usually refers to the spatial variable.
Yes, the x variable. Yes,
Okay.
yes, and that's a very important point. I want everyone to really think about that. These aren't just equivalent or interchangeable connections. These have to do with 2 fundamentally different, aspects of our reality, space and time, right? So yeah, So it's tricky. This stuff I think is tricky, you know. Okay, so here, let's think about what happens to the steady state solution for the case where we have insulated boundaries. Okay, something, I don't know if you can guess. I don't know if you can guess, but for the state of insulated boundaries, can you guess what does your intuition tell you the steady state temperature should be? Listen to your heart, people. If the boundaries are insulated, what do you expect? So you think about that. Okay, so as before, it is all the same temperature, but which temperature will it be? If I know the initial temperature is f of x, so if I have a piece of pizza and one end of the slice is 50 degrees, I don't know pizza temp, I don't know temperatures. One end of the slice is 6. Yes, that's right, Brian. So Brian in the chat said we would expect the equilibrium temperature to be the average temperature, right? If I have a slice of pizza and one end is 50 degrees and the other end is 0 degrees, I'd expect it to average out to 25 degrees. Yeah, so let's see that mathematically. I mean, I think physically that makes sense. And so let's see it mathematically. And so, okay, as before, I assume u is not a function of t, and I need to remember to fix that typo on the other slide. And then we integrate, so we get our usual linear solution here with 2 free constants. Now look what happens when we apply the boundary conditions. The boundary conditions aren't as useful as you think. So here when we, so the, you know, the PDE becomes a DE. Okay, so here I'm going to just take a regular derivative here because I want to use this piece of information here, and here now you use just a function of x, so the partial derivative just becomes a regular derivative. And so we take the derivative of our solution, we get it C1, but according to the information that's given, it's equal to 0. So we get this first constant C1 here is 0. So right now our steady state solution just looks like the constant u of x equal to C2. And now if you try to use the second piece of information, it doesn't help. If I take the derivative of this in an attempt to use this piece of information, well, the derivative is just 0. So we need to do a little more math here. Okay, so we still have one free constant, and it turns out that 2 insulated boundaries, you know, this is why this is a slightly different problem from the Dirichlet conditions, from, you know, when you have information about u. Okay, so here what we expect is, you know, our steady state temperature to look like, to be the limit of uxt as t goes to infinity. Here we're assuming our function temperature is not a function of time. And so if we send t to infinity, it's just going to equal this constant. So here we're expecting our steady state solution to be some type of constant. That constant is going to be the average temperature of f of x. Okay, so now let's see how this comes about. So here, now we're going to do a little bit of analysis. Okay, so, you know, just follow the steps. This is just kind of a one-time thing. I wouldn't worry about it too much. Okay, so what I want to do is rewrite the original heat equation so that I can take advantage of this information. So what you have to keep in mind always is that when you're doing research in math, or when you're trying to get results in math, it's about being sneaky. You have to look at what you're given, look at what you have, and find a way to make those match. And that's the magic, you know, that's the thing where you're banging your head against the wall, you're trying, and you drink too much coffee, then you wake up in the middle of the night hallucinating and you figure it out, you know. That's the story of how the guy figured out the structure of carbon-60, hallucinated off of too much coffee or something like that. I don't drink coffee, I'm not a caffeine person. So rewriting the original equation. So here's the original heat equation with the heat capacity term, the density term, you know, the case of 0 term from Fourier's law. So what we do is we divide k sub 0 by c and rho and rewrite that as a little k. Here, I don't want to do that because I still want to physically interpret what's happening. Okay, so I'm going to at some point multiply everything by an area and go back to talk about heat energy. Okay, so starting with the original heat equation, where C is the heat capacity of the material, the rod, the rho is the density of the rod, U is the temperature, K sub 0 here, that's our, that's the constant that regulates how the thermal, the heat flux is moving. Okay, so here, let's integrate both sides, because this was an integral equation originally. And now, here's the trick we're going to use. I'm going to do one integration here. Because if I integrate this once, that gets me to partial u. So the k sub 0 is a constant. You can pull the k sub 0 out. So pull the k sub 0 out. Integrate this one time, it becomes partial u partial x, and then we evaluate that, f of b minus f of a. So partial u partial x evaluated at L minus partial u partial x evaluated at 0. So here I did one integration from here to here. And now, we can now take advantage. We can now use the information, the boundary information. We're given that partial u partial x on the right side of the rod is 0. And we're given that partial u, partial x on the left side of the rod is 0. So I get this integral here equals 0. But what is this integral? So actually, to interpret this, we should multiply in the area and get this to look like a volume, and then we can actually interpret this integral as the heat energy. So look, multiply in the area. So here I multiplied in the area. And now pull out the derivative. Let's just say we can do that. There's a lot of analysis involved there. And so what we have, this integral on the left-hand side of our equation now looks like the integral for the total thermal energy. And so we know the integral is 0. So we know the rate of change of the total thermal energy with respect to time is 0. So this is some tricky analysis that we just did. This is something that they didn't just come up with in 5 minutes. So it'll take us, a little more time to appreciate the math here. And this is the type of analysis that we do in PDEs. This is the type of math trickery that's employed in PDEs, and a lot of use of integration by parts, as you may or may not have noticed. So here we didn't need any IBP, but that's kind of part of the analysis in PDEs. So, a lot of applied mathematicians, and this is what I always heard when I was graduate school, that integration by parts is the most important formula for an applied mathematician. I began to see why when I started doing PDEs, like, oh, okay. And a lot of these formulas that have different names, Green's formula and blah, 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 they're actually just integration by parts, Anyway, so here we come to the conclusion that the total energy, the time derivative of the total thermal energy is 0. So that means the total thermal energy is not dependent on time. It's constant with respect to time. So what? Well, we're trying to find the equilibrium solution. We're trying to say what happens to the thermal energy for large T. If it's time independent, here's the whole point of the analysis on the slide. If the total thermal energy is time independent, then the initial thermal energy must be equal to the final thermal energy. And look, I can calculate this integral inside here. I can use this to calculate the initial and final thermal energy. For the initial thermal energy, I just replace T with 0. That integral will calculate the initial thermal energy. For the final thermal energy, I take a limit and send T to infinity. What happens to U of xt as T goes to infinity? We know it equals this constant C2. So now I can set the left-hand side of the equation equal to the right-hand side of the equation and solve for the constant C2. and it should equal the average temperature, the average initial temperature. Okay, so let's calculate the initial thermal energy when T equals 0. I'm going to take that integral that calculates the total energy and plug in 0 for T. Now the initial condition kicks in. Whoops. We're given that U of X sub 0, the initial condition is U of X sub 0 equals F of X. So I replace U of X sub 0 with F of X. Now let's calculate the final thermal energy, the long time, the big time thermal energy. So here I'm going to take a limit of the integral as T goes to infinity. So here, this integral is calculating the total thermal energy, and we're sending T to infinity. Now, without asking too many questions, I slip the limit inside the integral and quietly assume I can do that. Don't ask any questions. Just look the other way, please. It's some trickery, some analysis trickery involved here. And those of you taking, 44 or 40, the analysis class, you'll probably get into this. And yeah, there's all kinds of stuff involved. I don't get it. Okay. So once we take the limit, this limit we know, we calculated, we tried to calculate as T goes to infinity, we have showed that goes to C2. That goes to C2. And now you can pull C2 out, it's just a constant, and you can actually calculate the integral. And so I can just get that it's, just the integral is just, if you pull out all the constants, the integral is just the length of the rod. So don't forget what we're trying to do here. I'm trying to find C2. C2 is unknown. So now I can equate the initial temperature and the final temperature. That's what the analysis on the previous slide told us, that we can equate the initial temperature and the final temperature. And again, don't forget what we're trying to do. I'm trying to find C2. Solving for C2, we get, and remember C2 is the final equilibrium temperature. That was our U bar of X equals C2. We get C2 is this formula 1 over L integral 0 to L f of X dx, which we know from calculus to be the average value of the function. So here with insulated boundaries, after a long time, the equilibrium solution, we expect it to be the average value of the initial temperature f of X, over the, as a function of the length of the rod. Yeah, so here is the solution to this, the thermal equilibrium solution for the situation where we have these insulated boundaries. And by the way, it's a complete coincidence that the first term of the Fourier series is also the average of the function. That's a total coincidence. I don't want you to think they're connected at all, just because this is a Fourier series class. They're not at all connected, absolutely not connected. I'm just kidding, right? Of course they're connected. This is no coincidence. This is the emergence of a Fourier series. We just, if we're Fourier trying to solve this problem, not knowing about Fourier series, Fourier doesn't know it, but we know this is foreshadowing. In the story, we know this is the Loch Ness monster showing, just a little bit tip of its tail, or tip of its head, if you will. So yeah, you'll start to see now when we solve the transient solution that the rest of the Fourier series will start to arise naturally. So let me switch over to the next set of slides. I have about 10 or 12 minutes, but I think I can just get them done because there's no math in the next set of slides is a review of what we've done. We just want to generalize the heat equations at 2D and 3D. So now we have one final detour before we actually start solving a PDE. Section 1.5 is the last section of chapter 1 in Haberman's book. In Haberman's book, starting in chapter 2, they start to solve the PDE. Okay, so what we want, this is just a kind of just a comment, and I don't want you to think that we're going to, and here's my preliminary remarks about moving the derivative. Again, we're going to move the derivative willy-nilly inside and outside the integral. Willy-nilly was the name of my chemistry lab partner in college. So here we just want to give the generalized version of the heat equation. So remember, our heat equation is on a rod. So what does that mean? The only direction, so for our one-dimensional heat equation, the only direction we can move in is back and forth along the rod. So what if, how about I want a two-dimensional version? So the two-dimensional version, we draw this a little bigger, two-dimensional version, we'd have a rod like this, where you could move in the x-axis up and down the rod, and then you could move left and right. That would be the two-dimensional version. So now you have x and y. And then what's the three-dimensional version? So let me draw the three-dimensional version. The three-dimensional version, now we have the x-axis, you can move back and forth here. Sorry, let me put in the sides of the rod, my bad. So you have the x-axis, you can move in that direction. You also have the y-axis, you can move, along the rod, you can move left and right. And we now also have the z direction. So now you have x, y, z. Your heat flux, has more, it can point in infinitely many directions in 3D. So we want to generalize from 1D model to the 2D model to the 3D model. Okay, and when we solve the PDE, please keep in mind, I don't want you to be intimidated by this stuff. We're gonna solve the PDE in 1D. We're gonna solve the wave equation in 1D. We'll solve Laplace's equation in 2D, and we'll use polar coordinates. Okay, but as far as the 3D stuff, this is just FYI. I mean, but you should know the 3D formulation of the heat equation, because that's just the most general form that will give you any dimension. So okay, so here we still use the same model. Rate of change of heat energy with respect to time inside the rod is due to heat energy flowing across the boundaries, or due to heat energy generated inside the rod. So here our heat flux is now a vector. So here I have cap phi hat of x. X is in boldface. This is either xy in 2D or xyz, or of course could be one dimensional, but that's not interesting. So here that's xy. Okay, folks. So please, here, we're basically just looking at the Calc 3 version of this problem, right? Where the derivatives will get replaced with gradients, and these, certain things will become vectors, or xyz. Okay, so here, if we have some solid region R, okay, and the surface of R is given by this notation. So this is a very common notation for the surface R. It looks like a partial, but when R is a surface, it's understood that notation is, when R is a solid region, it's understood that notation is referring to a surface. So this would be the surface of R. And so we can calculate Fourier's law, or we can calculate the heat flux across the boundary using this integral. So let's take a look at this integral very carefully, okay? So first look at the phi dot n part. So suppose phi is positive here. So here we've got this heat flux that's flowing out of our object. And so what we're doing is we're taking the dot product with respect to n. So what I'm doing is I'm finding the component of the heat that's leaving in the normal direction. And I'm doing this for every little square patch here on the surface. So on the surface here, for every little square patch, we're finding the heat flux that's leaving in the normal direction. And then we're multiplying that heat flux that's flowing out in the normal direction by the surface area. We're multiplying by the surface area. If you look at the units of the heat flux, it's heat energy flowing per unit time per surface area. So I multiply by surface area here So now I have the heat energy flowing per unit time across the entire surface of the object. Then we add it all together, right? That's what the integral does. So then with the integral, I sum it, so I have the total contribution, across the entire surface. I sum it. And the minus sign is for conceptual reasons. It has to do with the direction of heat flow and stuff like that. And, I'll let you read this here. I make a little comment down here about that. So yeah, we can now, write the heat flow process as a math equation. So here's that sentence now. The rate of change of the heat energy with respect to time is equal to, any heat energy flowing across the boundary plus, any internal sources of energy being generated. So this is the same model. Everything is the same, except we've generalized the spatial variables. Instead of just x, now it's x and y. And some things are vectors. And here we're doing a triple integral because, we're in x, y, and z, So now we can use the divergence theorem to rewrite this integral. This integral is the problem. We'd really like this integral here, which is a surface integral, to be a triple integral like this. And so we reviewed divergence theorem, which is basically a version of the fundamental theorem of calculus. Remember, fundamental theorem says integral of capital F prime, a to b, equals f of b minus f of a. Okay, so here, this is basically the same thing. Think of this part as the integral of the derivative. And then this is the surface integral part. In the 1D case, our surface are just literally the edges of our interval. And the outward pointing normal in this case would be the number 1. Here would be -1. And so that's where the minus sign comes from here when you do f of b minus f of a. So it's just a fundamental theorem of calculus where we're calculating, we're using information about the derivative inside the region to say something about what's happening on the surface, or vice versa, but, So we're able to replace that surface integral with this triple integral. And you get the divergence in there, the derivative basically. And so now we can combine all the interests. So big picture here is that this surface integral now looks like all the other integrals. That's at the end of the day, that's what's happened mathematically. So now I bring everything over, combine it into a single integral, and based on the analysis conclude, because this equation holds for any region R, conclude that the only way this is possible is if the integrand is directly 0. So once I replace this phi with a function of the temperature, we'll have our generalized model. And we can again use Fourier's law to do that. So Fourier's law of heat conduction, and let me just finish this up and I'll stop. Fourier's law of heat conduction here, says that heat flows from hot to cold. Mathematically in this scenario, we describe it this way. The heat flux vector is equal to negative k sub 0 times the gradient. Remember, the gradient represents the direction of greatest increase. In this case, it's increase of temperature, but the heat flux flows in the opposite direction, right? The heat flux goes from greatest temperature to lowest temperature. So the heat flux direction is, innately in the opposite direction of the gradient, just based on the gradient geometric, what it's doing versus the heat flux physically what it's doing. The gradient goes from smallest to largest, but the heat flux travels in the direction of, highest temperature to lowest temperature. That's why there's a minus sign there. And so now if we take the divergence of our heat flux, because that's what appears in our equation on the previous slide, we can replace the heat flux term with the term involving the temperature. So here I replace the heat flux with, it's what the Fourier's law of heat conduction says it's equal to. The heat flux is proportional to the temperature difference. And then pull out the k sub 0, and here you take the divergence of the divergence. That's also known as Laplace U. So here, the divergence of the divergence, or this thing, del u here is known as the Laplacian. And you can see in the 1D case, it just looks like would look like just our original heat equation in the 1D case. So here's our heat equation. When we replace phi, so here I replaced phi. The flux here gets replaced with this, right? This term. And now, you know, if you put the time derivative on one side, the spatial derivatives and internal source of energy on the other side, here's the most general version of the heat equation. And this should look like the 1D version. The only difference in the 1D version is here, is right here. Instead of this del, we have this just second partial with respect to x in our 1D version. Otherwise, it more or less looks the same. I mean, we don't have bold-faced x. In the 1D version, we just have x is not, you know, a point in space, it's a point on line. So yeah, and if you assume q is equal to 0, here's and then, you know, assume all the coefficients are constant and then divide just to get the, here's our most generic form of the heat equation. And that should work in any D. And of course, the initial condition will look like that, where x is, you know, xy or xyz, depending how many input. And the boundary condition will look like that, where we're specifying the temperature on the boundary surface. So this specifies the temperature for x on the surface. So, you know, when you do the higher dimensional problems, it becomes more and more complicated just formulating the problem. What does a boundary condition look like? What do the initial conditions look like? So these problems get exponentially difficult in PDEs. You know, that's why we say PDEs is so difficult. All right, everybody, I've come to the end here. The next slide, you know, is just some variations on what happens if we assume certain parts are 0. And I'll do this next time, but we can get Poisson's equation if we assume U is not dependent on time. And then if we assume you have no internal source of energy, we get what's known as Laplace's equation, which is very, very famous in stability analysis. And then I'll give it to you in cylindrical coordinates, but you already know this because you did it in the homework, in that horrible chain rule problem on homework 1. And then I'll give you the spherical version of it. And, you know, so I just basically did what I just did. I'll just do that. And then we'll finally start solving the transient solution to a PDE using separation of variables. And finally, in some sense, on Wednesday, the class will actually start. All of this up until now has been pre-start. All right, everybody, I'm going to stop right here. I want to thank you for your time.